family of superspirals with completely monotonic curvature, given in terms of Gauss hypergeometric function. This presentation is prepared for International Conference on Geometric Modeling and Processing. Let me firstly introduce myself. My name is Rushan, and I am the citizen of Russia. I have got my PhD degree in mathematical modeling, computation methods, and program systems from Lyanovsk State University, Russia. My previous research area was connected with mathematical models in cosmology and gravity. My present research interests are geometric modeling, computer-aided geometric design, especially spirals, spiral splines, aesthetic shape modeling. Nowadays I continue my research in the most international university of Turkey. Motivation. The present work was motivated by an opportunity of finding a very general analytic way in which so-called fair curves can be represented. The possibility to generate fair curves and surfaces that are visually pleasing is significant in computer graphics, computer-aided design, and other geometric modeling applications. So, what is the fair curve? A curve's fairness is usually associated with its monotonically varying curvature, even though this concept still remains insufficiently defined. So, here we give some examples of fair curves. Well-known spirals like logarithmic, Nielsen spirals, and involutes of a circle. The research on these spirals was performed by Cook, Meek and Walton, Harari and Tell. Class A Bezier curve, Gerard Fairing. Pythagorean holograph quintic spiral, Walton and Meek, Faruqi. Spirals obtained by inversion of hyperbola and parabola, Alexei Kronrod. According to the author of this work, a series of interesting works of Alexei Kronrod play an important role in the research on spirals. Log-aesthetic curves, Harari, Miller, Yeshida and Zlatdinov. Generalized log-aesthetic curves, Gobiat-Hassan and Miller. Superspirals, Zlatdinov. Moreover, in the following works the curvature monotonicity conditions for a planar curve were studied. The study of spirals in nature have a long history. Christopher Wren observed that many shells form a logarithmic spiral. Jan Sawamedem observed the common mathematical characteristics of a wide range of shells, from helix to spirilla. Darcy Thompson's work titled On Growth and Form gives extensive treatment to these spirals. He describes how shells are formed by rotating a closed curve around a fixed axis. The shape of the curve remains fixed, but its size grows in a geometric progression. In some shell, such as Nautilus and Ammonites, the generating curve revolves in a plane perpendicular to the axis, and the shell will form a planar discoid shape. Thomson also studied spirals occurring in horns, teeth, claws and plants. So, spirals can be considered as an important component of natural world objects. Horns, seashells, bones, leaves, flowers, and tree trunks. They can also be used as transition curves in railroad and highway design, in fillet modeling, as well as font design. This slide shows some applications of spirals. In this paper, we consider a radius of curvature function of a planar curve in terms of a very general, Gauss hypergeometric function which is completely monotonic, under some constraints. This allows us to enclose many well-known spirals, the family of log-aesthetic curves, and other types of curves with monotone curvature. The properties of such a curves can be still remain unexplored because of the curve's complicated analytic expression in terms of special functions. The Gauss hypergeometric function is an analytical function of a, b, c, z, which is defined in C4, as written in Formula 1. Here, the Pochhammer symbol is defined as it's shown in Formula 2. In the general case, where the parameters have arbitrary values, the analytic continuation of f, a, b, c, z, into the plane, cut from 1 to infinity, can be written as a Cantor integral, also known as the Barnes integral, shown by Formula 3. Here gamma function is defined as in Formula 4. A complete table of analytic continuation formulas for the Gauss hypergeometric function which allow its fast and accurate computation for arbitrary values of z and of the parameters a, b, c can be found in the paper of Becken and Smelcher. Formulas 6 and 7 show several specific values of the Gauss hypergeometric function in which we are interested. Besides the Gauss hypergeometric function, the function, which is called a confluent hypergeometric function, plays an important role in special functions theory. It is represented by Formula 8, and here a to the power of n is known as rising factorial. The Gaussian hypergeometric function is the generalization of many well-known functions, such as power, exponential, logarithmic, gamma, error, and inverse trigonometric functions, and elliptic, Fresnel, exponential integrals, as well as Hermite, Leib-error, Chebyshev, and Jacobi polynomials. The functions discussed above play an important role in mathematical analysis and its applications. The family of superspirals, Miller and Samko, have shown that Gauss hypergeometric function is completely monotonic for c greater than b greater than 0, and when tangent angle theta is greater or equal to 0. The radius of curvature of logisthetic curves is shown in Formula 9. Formula 10 extends this function. For the case when alpha is equal to 1, Thomas function is used. We present the new definition in this work. Definition 1. A superspiral is a planar curve with a completely monotone radius of curvature, given as Gauss hypergeometric function, where c is greater than b greater than 0 and a is greater than 0. Its corresponding parametric equation in terms of the tangent angle is defined by Formula 11. The arc length of the parametric curve, 11, can be obtained from well-known indifferential geometry relationship, and after integration of the Gauss hypergeometric function, we obtain equation 12, which relates the arc length with the tangent angle, is often called the Fuel equation. We are interested in the non-negative values of the tangent angle, since the restrictions mentioned above, and this makes the properties of a superspiral to be, as discussed below. A superspiral is always passing via the origin point, where tangent angle equals to 0. X-axis is a line tangent to a spiral at the origin. For fixed a, b, c, in non-polynomial cases, a superspiral has no singularities. Absence of upper or lower bounds for tangent angle, strictly monotone curvature. This slide shows two examples of superspirals and their curvature functions for different values of a, b, and c. Tangent angle is varying from 0 to 10 pi. Finally, equation 11 was expressed in terms of infinite series. For practical cases, when tangent angle is not more than pi radians, these equations may help us to represent superspirals in polynomial form, which is more convenient for CAD systems. In our paper, we have also presented asymptotic equations for small values of tangent angle. Please refer to our published paper for more detailed information. As we mentioned above, superspirals can be applied to fillet modeling, and below, some examples are shown. Figure 3a shows an example of fillet modeling. A G1 transition superspiral between two straight lines is generated by the Yeshida-Sato method, and swept along the z axis to obtain a transition surface between the two planes. The same surface with generated zebra lines is shown on Figure 3b. In the following figures, one may see the surfaces of revolution, which are applicable to computer-aided design of, for example, canal or pipe surfaces. The resulting surface therefore always has azimuth orthometry. The following definition refers to these surfaces. Definition 2. A superspiraloid is a surface generated by rotating a two-dimensional superspiral curved segment about an axis. Conclusions and future work. We have introduced analytic, parametric equations for superspirals, whose radius of curvature is given by Gauss hypergeometric functions, which are completely monotonic under described conditions. Whereas previous authors deal with the specific curves having linear curvature graphs, the superspirals can cover a huge variety of fair curves. Proposed superspirals can logically be applied for generating nonlinear spliners using the Yeshida-Satho method for two-point G1 Hermite interpolation, as well as for constructing nonlinear spline with curvature continuity, which is actually G2 multispiral, the generating algorithm for which would be the scope of our next works. Finally, we would like to extend this approach to generate superspiral space curved segments and three-dimensional superspiral spliners.